So in the previous lesson that you didn't have any questions on, we talked about the absolute values of numbers. And that's just to warm you up to the idea of what absolute value means. What we're going to be looking at today is the absolute value of a function. Not the absolute value of a number, but the absolute value of the graph of a function. We're going to be graphing linear and quadratic absolute value functions. In other words, since a linear function is a function of this form, I'm saying at the end of today, you will know how to graph functions that look like this, equation-wise. You already know how to graph functions that are quadratic functions. I'm saying by the end of today, you will understand how to graph the absolute value of a quadratic function. And I'm going to go even so far as to say this. Even though we're learning about linear and the absolute value of linear functions, and quadratic and the absolute value of quadratic functions, I will say in general that if you know what any function looks like on a graph, even though you don't have the equation, maybe I just show you the graph of it, you should know what the graph of that looks like. So there's a connection between what the graph of a function looks like and what the graph of the absolute value of that function looks like. But the reason why we have these two that we like to talk about is that in grade 10, you learn a lot about linear functions, and in grade 11, we learn a lot about quadratic functions. But this can be applied to any function. So as a warm-up, consider the functions f of x equals x and g of x equals the absolute value of x. And this, I've really struggled over the years on how I can avoid a problem here. And I don't think I can. I think it's just difficult to understand. I would like you to understand that when I say that we have a function f of x equals x, and then I say g of x is the absolute value of x, what I am saying is that g of x is the absolute value of f of x. And that can be confusing because it's not really a necessary statement. I started off by telling you we're looking at graphing functions and the absolute values of those functions. So what we're talking about in this warm-up, another way to look at this, is we are talking about graphing y equals f of x and y equals the absolute value of f of x. And I understand the function notation can be confusing. But whatever, I'm going to explain this in detail. You guys are smart enough to follow this. I know that. That I told you over here, if you know what a graph of a function looks like, you should be able to figure out what the graph of the absolute value looks like. So there's something that you do to this to get the graph of that. It's the same thing that you do to this to get the graph of that. It's the same thing that you do to this to get the graph of that. And what we're learning in the warm-up is, what is it you do to the graph to get the new graph? What is it you do to f of x to get g of x? Okay. F of x is the linear function with no absolute value signs. G of x is the absolute value of that linear function. Okay. So we're going to complete a table of values, and this seems so trivial and so simple that you're going to lose the thread of what I'm talking about here on the left for a bit, but that's okay. Y equals f of x. What is the y coordinate on the function f of x when x is negative 3? Well, it's negative 3. Because the original function is right here. This is the original function. which means if we replace the function notation, you can just write y equals x. It's a very boring function. Every point on the function f of x has an x and a y coordinate that are equal because the rule for that function is y equals x. So we can fill this in. This is -2. This is -1. This is 0. This is 1. This is 2. This is 3. And again, I struggle with this because many of you will think I'm making things intentionally more confusing than they need to be, and it's not my intention. If I say what is the y coordinate on g of x, I'm talking about this function. I'm talking about y equals the absolute value of x. But this is f of x. G of x is y is the absolute value of x. So I know that you could look over here at this and say the absolute value is 3. I know that. But what I'm asking you to do is look here instead. Because the big idea is that g of x, and don't forget, y is always the function. So when I say g of x, I mean the y coordinate on g. That g of x is the absolute value of whatever f of x is. So I'm asking you to look here, even though the numbers are the same. So this, I'm thinking, or asking you to look at this way. Whoops. And f of x and f of x is this column. Do you get the subtlety of what I'm talking about here? I know it's the absolute value of x, but in this case it's the absolute value of the y coordinate on f of x. So these become 3's, 2, 1. They become the absolute value of the old y coordinate. And I can reveal to you now what we're doing in general. When we are going, and I'm going to change how I write this. When we are going from a function to the absolute value of the function, what we are doing is taking every point on the function and changing it to that. All we're doing is we're taking the absolute value of y, because the function that we're absolute valuing, if that is such a way to say it, is really the y coordinate of the original function. And this idea is very important. This is called mapping, and although mapping is not in the curriculum for Math 20, it's visited dozens of times in Math 30. So if you happen to see it here when you get to Math 30 and your teacher talks about mapping, you understand what you're talking about. Mapping shows what happens to the coordinates of a point. So in this first warm-up, this point here on f of x this point of -3 comma -3 becomes, on the new function, -3 comma +3, because we are taking the absolute value of the y coordinate on the original point, or on the original function. So we've completed the table of values, and this idea of this mapping being x comma y turns into x comma absolute value of y will become more obvious in the next example, hopefully. So now what we want to do is we want to sketch these. So I've got my data table up here. I want you to notice that when y was negative on f of x, we multiplied it by -1 to make it positive on g of x. but when y was positive, we left it alone. That's what I meant earlier when I said the absolute value of a number is the number if the number is positive, and the absolute value of a number is the negative of that number if the number was originally negative. So we're going to plot these points. I'm going to give you rulers so that we can plot them in a human-like manner. Nice and tidy. You should already know what y equals x looks like. It's a straight line with a slope of 1 through the origin. There you go. If I plot some points to help us out here, 0, 0, 2, 2, 4, 4. They don't have to be points from our data table. That's not what's important. In fact, I hope you agree you don't need a data table to know what this graph looks like. Let's not worry why I'm drawing the line so thick. That's not important. It will become important for you in a second. And I'm not going to worry about putting arrowheads on the end of that line. We know that it continues forever. I used to be a real nitpicker about putting arrowheads, but I see on diploma exams now very often they don't have them. In other words, you're expected to know that this line goes on forever. Now, what about plotting these other points? Well, let's start with this one. Where that green dot is on the right side of the table, that represents the point -2, 2. Right? So if I plot that point, -2, 2, it's here. What if I go to this point? Well, this would be the x-coordinate is -3, and the y-coordinate is 3. I hope you understand that when we're talking about g of x, we're looking at this column and this column, right? Okay. So we can plot that point. And we can do the same thing, if we like, for -4, 4. Even though it's not in our data table, I hope you realize that -4, 4 will be a point on g of x. And I'm not putting every single point. We can put the origin as well. Well, maybe I will put a lot of points. I'm not putting every point because there's an infinite number. So, do you agree that the first 4 green points left to right do not match up with where those corresponding points were on the original function? But the green dot in the dead center of our grid does match up with what we started off with. Yes? Okay. And every other point to the right will line up as well. So if I were to sketch this graph now, would look like this. This is why I made that red line thicker, because what we are looking at here for one part of this picture are two lines that are on top of each other. Now, I don't know how you're going to communicate that when you draw this, but take a minute if you haven't drawn it already and sketch the absolute value function. So the red one is y equals f of x. The green one is called g of x, and it's the absolute value of f of x. I'm going to give you a second to catch up with what I've written, and then I want to go through something again with you. So one of the things I want to talk about here is I could be specific. Rather than writing what I wrote, which is y equals f of x, and g of x is the absolute value of f of x, I could have written y equals x, and g of x equals the absolute value of x. But I know, again, I sound so repetitive here. The point is that g of x, let me start again. The point is not that g of x is the absolute value of x. The point is that g of x is the absolute value of f of x, which happens to be x. Are you with me on that? Okay. So, by the way, we could graph these on our graphing calculator, which apparently I'm going to have to move somewhere else. Go ahead and go to your y equals and enter y equals x, and then y equals the absolute value of x. I showed you yesterday how to access the absolute value function on your calculator. So y is equal to x, and y is equal to, you go math over to number, absolute value of x. Now, do you agree that these two lines are at 45 degrees? All of the lines are at 45 degrees. When you go zoom standard, it will not look like it's at 45 degrees because zoom standard, if you look at my hands, goes from negative 10 to 10 horizontally and negative 10 to 10 vertically. But your screen is not a square. Your screen is rectangular. If you want to look at it so that it's scaled exactly the same way horizontally as vertically, then you go zoom square, zoom 5. It's not going to magically change your screen to a square, but it will scale it in a square-like fashion. So that this distance on your calculator horizontally, if that's 10, it will put the same distance as being 10 vertically. And you can see that that's what it looks like. If you looked away like I did, have I shown you the little bouncy ball? Okay. The bouncy ball is nice for a second function to follow it. Oh, hate it when I go past. So now it's going to graph it from the beginning again. There's y equals x. Here comes the absolute value of x. Poing, and it bounces up. Okay. But let's talk about the general idea of what's going on here. Well, I'll ask you, why is this section of the graph not the same as the corresponding section in that domain? When I say in that domain, I mean for x equals negative numbers. Why is that green section that I've highlighted in a big thick green line, why is that not matching up with the corresponding red section of the original? Colin?
All the negative values of y become positive.
Of y, right? So any place the y coordinates on the original are negative, they get bounced up above the x-axis. And, I know you know this, but these distances are the same, aren't they? It's a nice reflection is what it is. And that's what's happening. That's how you take a graph of a function and turn it into the absolute value function. So describe how the graphs are related. Well, whenever f of x is greater than or equal to 0, g of x is the same. what I mean by this, I'll start with this. What I mean by this is y on the function f of x. Whenever the y coordinate on f of x, which I can just call f of x, that's what y is. You might even remember from last year when you were introduced to function notation, your teacher might have said, don't worry about it, you see f of x, change it to y, right? And that's what we teach you initially to get you to become accustomed to it. It's the y coordinate. And this is the y coordinate on g of x. So if the y coordinate is positive, leave it alone, leave the point alone. Whenever f of x is negative, g of x, well, we can say a lot of things here. We can say g of x is multiplied by -1, which takes me back to where I started today's lesson. Or we can say g of x is reflected above the x-axis. And this is equivalent to what I said. The absolute, except I'm not going to say the absolute value of a number. The absolute value of a thing is that thing if the thing was positive. The absolute value of a thing is negative of the thing if the thing was negative. We could even write that out here in the hopes that you will see it enough that if you don't understand this now, you will understand it more and more later. Starting to get into some conceptual ideas here, not just numbers or graphing or stuff like that. The absolute value of f of x is f of x if f of x was greater than or equal to 0. Another way to look at this, everybody, is if f of x is greater than or equal to 0, then you don't need the absolute value signs. But the absolute value of f of x is negative f of x if f of x was negative. I hope you would agree that in this region here, f of x is negative. So you take f of x, every y coordinate, and you multiply by -1, making it positive. It's a pretty weird idea. Well, it's a simple idea. It's a weird way of explaining it. So this, if you look at this, this would be a grade 10 student would walk into the classroom and look at what's in that box and go, I don't know what that means. You should know what that means. Let's look at the next one. Complete a table of values by writing the values of the y coordinate for each of the two functions. Let's use our calculator. We may even, I haven't decided, use our calculator to generate the graphs. Okay. So how am I going to generate the table of values? I'm going to go y equals and enter 0.5x squared minus x minus 4. I'm going to go to my table setup and start at -3 and go up by 1. Second window, start at -3, go up by 1. I don't often do this, but maybe it's good that sometimes I do. I don't even think we need to necessarily write anything down here to learn from this example. I am recording this, so if you want to watch it again later, you certainly can. What does our table of values look like? Well, those are the numbers, okay? Those are the numbers. I've already got them up here. If you want to write them in, you certainly can. And I see that it actually goes up to 5 on yours, doesn't it? I feel as though I want to show something to you, and it might eat up a couple more minutes, but I think it will be valuable. I'll give you a minute to write down all of the numbers. You understand that the absolute values will be all positives. So, I hope you understand, and I'll write it up here, that h of x is the absolute value of f of x. If we take a look at h of x, it's the absolute value of 1/2 x squared minus x minus 4, but that's f of x, right? So I think you appreciate how we're getting this set of numbers in the third column up here, yes? But I want you to look up here now. I could, and don't worry about memorizing how this works. If you find a use for it later, I can teach it to you again. I don't have to put, rats, 0.5 x squared minus x minus 4. I don't have to put the absolute value and type that whole thing in. I can put the absolute value of y1. If I go to variables, it's vars, and I go over to y vars, and I hit function, and I choose y1, I can put that in there. And this reinforces the idea. Look up here. y1 equals 0.5 x squared minus x minus 4. It's the y coordinate. y1. So when I do absolute value of y1, it gives me those numbers. So I am going to shave off a little bit of time here, and I'm going to not plot the points. You could, and it would take you a little while, but I don't think we need to. Let me graph and follow along carefully up here. I am going to turn off y2. I scroll over to the equal sign of y2, and if I hit enter, it turns it off. I don't know if you knew that you could do that. Now when I go graph, we are looking only at y1. And I'm going to, we've talked about this numerous times. Well, maybe not. Do you agree that this is kind of wasted space? And so is this. So why don't I go from about negative 5, it looks like, to 6 or 7. That'll spread things out a bit. Window setting, negative 5 to 7. That's nicer. It's more gentle. It's not as ragged. Now what I'm going to do is turn on y2, and I want to go with the bouncy ball, because it slows things down and I can watch things. And again, when you do this, now when you go graph, it's going to start at the beginning and it's going to continue from all the way to the end. So I go graph, here, oh, it doesn't start again for some reason. So if you want to include a sketch, rather than sketching that graph on the grid that I've shown you, this is f of x, and I realize it's thicker in some places than others, but that's because I'm on a certain type of drawing tool. And this is g of x. Where are these graphs identical? They are identical wherever f of x was greater than or equal to 0. They're identical here and every place there. They're identical here and every place there, because that original graph, the red one, was on the x-axis or above the x-axis. Whereas I need to take, if you look up here now, I need to take this section of the graph that is below the x-axis. Not those 2 points. Those 2 points are on the x-axis and they didn't need to move. And I need to reflect it vertically to go there. Capiche? So which subdomains of the two graphs are similar? Where are these two graphs identical? Now, I hope you remember. You remember when we were talking about maxes and mins on parabolas? And I said, where does it happen? What am I asking you about when I say, where is the max? So if I have a parabola, don't worry about this picture on the left. If I have this parabola and the maximum has coordinates of 1, 10, and I say, where is the maximum? What's the answer? So you do forget. It's at x equals 1. Is that what you're going to say? And if I say, what is the maximum, you say 10. But when I say where something happens, I talk about x. So where are these two graphs identical? 1, 2, 3, 4. When x is greater than or equal to 4, they're identical. And when x is less than or equal to 2, they're identical. These are the same. The graphs of f of x and g of x are identical. Where are they different? Where is g of x negative f of x? In between 2 and 4. Because in between x equals 2 and x equals 4, f of x was negative. So we have to multiply it by negative 1 to change it positive. And finally, on the whole warm-up kind of set of problems, how do you obtain the graph of the absolute value of a function from the graph of a function? The answer is any part of the original function that's below the x-axis, you fold it above the x-axis. So if this is an original graph, if that's f of x, the absolute value of f of x will have the same x-intercepts, and everything that was above will still be above, but anything that was below gets folded above. It doesn't have to be perfect. Mine certainly isn't perfect, but you get the gist. And I think a picture is worth 1,000 words here. I don't think we need to write anything as we're learning about this. If I asked you about it on an exam, you might have to explain it a bit better. I'm really not happy with this middle part here, so I'm going to fix it a bit. That's almost worse, but you get the idea, right? Capiche? Okay. I want you to notice that the x-intercepts are always going to be the same. Will the y-intercept always be the same? This is a bad one to look at, but is the y-intercept the same here? Yep, the y-intercept is there for both. Does the y-intercept have to be the same? When would the y-intercept not be the same? Colin?
When it's negative.
Right, when the original y-intercept is negative, what's the new y-intercept? Just change the sign of it. Okay, let's turn the page now. Back to sketching. What does this graph look like? Well, it's a straight line with a slope of 2 and a y-intercept of negative 3. Basic math 10, right? The slope of this graph is 2. The y-intercept is negative 3. Well, let's start plotting some points. Negative 3, slope of 2 means you go over 1 and up 2, over 1 and up 2, over 1 and up 2. So take your ruler. And draw the function. I guess we can label this y equals 2x minus 3. What does this function look like? Well, it looks like this, wherever this is already on or above the x-axis. Because if the point is on the x-axis, the y-coordinate is 0, and the absolute value of 0 is still 0. What we are doing is we are saying that's what we're saying. That's all we're saying in this whole lesson. I mean, there's other things that it leads to. So if I were to plot, I'll use green for this one. I used red for this. This point, and this point, and this point, and this, all of these points would be the same. And these other ones would be reflected above. Why I can't get a green here. There we go. Green. Good? What is the domain and range? Well, just look at the graphs. The domain is x is any real number. The range is y is greater than or equal to 0. We're talking here about the domain and range of the absolute value function. And when you take a look at the green graph, it goes on forever left and right, but the lowest point is 0, so y is greater than or equal to 0. Somebody had asked me, and Mr. Hetlinger and I have been talking about this as well, there might be some real interesting rules you come up with for domain, but range is only ever found by looking at a graph. Okay. I think we're also asked for the intercepts. Well, forget about the absolute value. What is the x-intercept of this function before the absolute value? I hope you see it's 3 over 2, right? Okay, but when you take the absolute value of a function, the x-intercept stays the same. Because an x-intercept is where y is 0, it doesn't get flipped. So the x-intercept here is equal to 3/2. What's the y-intercept of this function? Well, that's where you let x equal 0, and you get the y-intercept is -3. So what's the y-intercept of the new function? Positive 3. Because it's the absolute value of y. Let's just learn with this one. I don't think we need to draw this. Let's use our graphing calculator to look at f of x, and then we'll put in g of x, make a prediction as to what it should look like, and then answer the rest of the questions. So negative brackets x plus 2 n brackets squared plus 4. I'm going to start with zoom standard. Looks like that. I'm going to shave off a little bit on the left and a little bit on the right. Zoom standard goes from negative 10 to 10, so I'm going to go from negative 6 to 4, I think, might do it. That's a pretty good one. So that is the graph of f of x. This is the answer to A. What should g of x look like? Well, it should have this in common with f of x, but this will be reflected up, and this will be reflected up. Should look like that. And again, rather than typing in the whole thing, I can enter for y2 the absolute value of y1. Now let's just see. How many of you remember where to go to find y1? VARs stands for variables. What kind of variable? It's a y variable. It's a function, y1. And I like to play around with this. Oh, missed it. I'm curious now. Wonder what this does. I think it just does the bouncy ball, but it doesn't leave a line. Is that what it does? Yeah. If you want to change it to the bouncy ball with the line. There it is. Well, let's use technology. Well, domain and range, okay, of g of x. Well, the domain is x is any real number. Don't forget, g of x is this red thing. What's the range? Y is greater than or equal to 0. It's not always going to be y is greater than or equal to 0. It's not, okay? If I gave you the following graph, I'm going to turn y2 off. This is a nice thing, by the way. Turn y2 off. I can put in a new function up here. I'm going to put in brackets x minus 2 n brackets squared plus 3. And I'm going to go zoom standard. And this is what it looks like. What will the absolute value of that function look like? It'd be the same thing, because everything is above the x-axis. If I turn on y2, what if I had this? What does the absolute value function look like? It looks like that. The whole thing gets flipped. It depends on the situation. We'll leave this one to you for you to think about. No. Never mind. I'm thinking of something else. Don't worry about it. What are the x and y intercepts? Well, I regret now removing this, so I've got to put it back in. It was negative bracket x plus 2 quantity squared plus 4. I believe I went from negative 6 to 4. Yeah. You can see the x-intercepts of the original function are negative 4 and 0. Those will be the x-intercepts of the absolute value. The y-intercept, well, what's the y-intercept of this function? I'm just going to go trace 0, trace 0, confirm that the y-intercept is 0. If the y-intercept of the original function is 0, the absolute value of 0 is still 0, so this y-intercept is 0. I mean, we finished this last lesson, or this last example, using a lot of technology. By the way, I never really have this graph on here, do I? G of x. This is f of x. Once again, I can turn this on, and here comes Did I not turn it on? I guess I didn't. There we go. And there comes g of x. Doesn't matter what the graph looks like. You fold what's below the axis above the x-axis. And that's it. So you don't have to do every question here. You've got about 15 minutes or so. Do a good collection of them, some from the beginning, some from the middle, some from the end.